All right. There are a few guarantees in life, but among them are, of course, death, taxes, and a lab question on the AP Physics exam. So these questions, they differ a lot in what's asked of you, but always you're going to be asked at some point to do some sort of a linearization or best fit analysis. But among the other tasks, you could have to derive an experiment, derive a model for an experiment, and or error analysis. And of course, most of these integrate multiple parts. So learning how to answer this style of question will definitely be crucial to your success on the exam because, well, you're guaranteed to have a design question. So the first thing you could be asked is to design an experiment. So these are just referred to as experimental design tasks, and it is up to you to outline the procedure that can be followed to determine some physics quantity. And in general, you're going to have to draw a diagram. You have to label what's being measured on it and how to measure those things. So you have to say what equipment's being used. And then you just say what steps you'd follow to collect the data, including how to minimize error and how you're going to analyze that data. So, if you're asked to design an experiment, first you got to decide on what experiment you're actually going to design. So, you should begin by identifying what quantity are you wishing to calculate. Is it the moment of inertia? Is it mu sub k? Is it acceleration? Is it g? And once you figure out what exactly you're trying to measure, you should write down any relevant physics equations and see if you can somehow figure out portions of that formula that allow you to solve for the unknown quantity. And once you find an equation in which all the other values can be measured or calculated, you got to determine a setup to basically give you everything else. Because if you want the thing to the left of the equal sign, that means that everything on the right has to be known. So you got to make sure you can measure everything else. So, on to measuring devices. Assume you have access to basically anything you'd need in a standard physics class. Don't underestimate your simple tools like meter sticks, scales, timers, etc. But of course, if you have access to them, smart carts can measure position, velocity, acceleration, force, time, but those have all the bells and whistles. So if you're asked just to design an experiment and you want the highest tech, most censored equipment, smart cars are really good there. But then old but tied and true is the photogate, which just tells you the velocity of any object passing underneath it. So if you want to find the velocity of something, photogates are typically your friend. And if you're using anything non-standard or even anything up here, just outline how it should be used. It's going to make you explain how the equipment is used, not just what equipment. So then for the diagram and the procedure, draw a labeled diagram of the setup. Just make sure to use the same variable names that you're going to be using later in any derivations of a formula. And explain how each variable will be measured. You either cite the measuring device you're going to use to measure it, or explain briefly how you got to calculate it. And then you just list the steps that someone can follow to collect all required data. Explain how you're going to minimize error, typically just by doing multiple trials. That's a good way to lower uncertainty. Doesn't fix any systematic errors, but it will reduce uncertainty overall. And then for your results, you just explain how you use the required data to solve for the quantity of interest. So you should list an equation that can be solved using the collected data. So it should have only the variables you actually collected in it. You don't necessarily need to solve it explicitly, but if you're studying a claim, it's going to be a bit different. Just clearly state what outcome either verifies or refutes the claim. If we find this result, that means the claim is valid. If we find this result, then the claim is invalid. So let's do an example. Suppose a group of students wish to calculate the coefficient of static friction between their shoe and a wooden plank. Your task is to outline an experimental procedure that the students could follow in order to determine the value of the static friction coefficient between their shoe and the wooden plank. First part, draw a diagram of the experimental setup, list all values that will be measured, and what equipment will be required. So here's a very typical setup for this experiment. There's definitely more. And other setups for this are going to look nothing like this one, likely. So if you thought of something else, as long as it all checks out in the end, it should be fine. But I'm going to take a ramp approach where you set up the shoe on a ramp, you slowly start tipping the plank until the shoe starts to slip. You record the length and height of the ramp at that time, and we're eventually after that angle. So we measure the total height h and length l of the wooden plank ramp. And we do this so that we can calculate this ramp angle down here just using inverse sine of h over l. Now let's talk about the procedure. So this one, we basically explained it already, but we have to make sure to clearly identify the steps that we're going to take to reduce the amount of uncertainty we have. So place the shoe on an initially flat wooden plank, measure the length L of the plank, then slowly raise the ramp angle until the shoe first begins to slip. Record this height h. Using the measured values, find the angle of the incline using theta equals inverse sine of h over L. We're going to repeat this multiple times. Find the different slip heights, find the angle every time, and just report the average ramp angle that causes slippage. And again, this is to reduce experimental uncertainty, because if we have multiple trials, chances are that we get better results if we do it more. And then for the actual derivation of this, showing that this experiment will work, it's all based on force balancing. So when the shoe first begins to slip, the down the ramp weight force has to be equal to static friction's maximum value. So it means static friction can no longer compete with the down the ramp force. So we just set up that the max value of static friction is equal to the force of gravity down the ramp. Max value of static friction is always mu times normal force. And the down the ramp force is mg, which is the whole weight times sine theta, gets you the down the ramp component. And then with a bit of algebra, we can simplify this to a very short mu is given by tan of the slip angle. So this is kind of a classic lab. This is a good one to know about. But this is probably a very easy way to get static friction coefficient. Again, there's other ways. You could take an Atwood machine approach. You could take a kinetic friction approach with the ramp. Actually, no, we can't do that because we want mu s. Another one, just to expand, would be to attach some sort of a rope to the shoe and do some sort of Atwood experiment until the shoe first begins to accelerate. The next task we gotta be able to do is linearization. Every lab-based question will contain a linearization section. You have to know how to do it. In this section, you gotta decide what relationship to graph typically. Sometimes they give you the relationship, but usually you gotta figure it out yourself. More recently, they've been giving you the model and just asking you to best fit with it, but you definitely should be able to derive it yourself. Luckily, though, if you're given the model, you can actually do this part without knowing any physics, which is very helpful if you're stuck on a problem and get to one where you actually don't need anything external. General strategy: figure out the linearization to use, graph that linearization, find the slope and intercept, and solve for the quantity of interest. So how do we decide what to graph? Well, if you're not given a model, then you have to use relevant physics equations and principles in order to derive an equation that has both the independent and dependent variables in it. They don't necessarily have to be solved for one or the other. It just has to be a physics equation in which both of the variables you want appear in there and nothing else that's changing. Once you have an equation, you got to determine some way to transform the data so that you can get it into this y equals mx plus b relationship. So let's look at some simple examples. So let's say you're given the distance an object has fallen h and the time it's been falling t. And Here's our model, h equals 1/2 gt squared. So this is definitely not linear because t is squared. So here's a possible solution. First thing you should do is clearly identify what things are the variables here and what things are constant. So I'm using red throughout this presentation. So h and t are my variables. So that means the thing I should graph involves h and t. And notice I can actually cleverly do some groupings here and get a straight line. So if I just graph h inside the box versus t squared inside the box, this fits in exactly y equals mx plus b relationship. So we can see the color coding here. It's linear with y being h and x being t squared, and the slope is going to be equal to half of g in this case. But a more precise way of seeing this would just be to send all the variables to one side. So h divided by t squared is equal to the rise over run, which is the slope, which is 1/2 g, which is more importantly a constant. And since the fact that the slope doesn't change, that means this is a straight line model. So therefore, h versus t squared is linear with slope 1/2 g. There are other linearizations you could do. You could graph t versus square root h. You will get a different slope. There are lots of different linearizations. It just has to be consistent with this one. So if you do those, you will get different slopes, but the end result will be the same. There's no preference to how you linearize, as long as it's valid. Here's a more complicated example where we got some more constant square roots in there. We're measuring the oscillation period t of a pendulum versus its length L. So the challenge here is that there's some stuff we might want to get at that's under that square root. So typically the first thing you do if you have a square root in your model is you just square both sides in order to get rid of the square root. Again, totally valid move. You could definitely graph t versus square root L and get a slope with a square root g in the bottom, but just to avoid dealing with square roots, let's square both sides. And notice I already color-coded my variables, so I know what's changing here. And now after a quick squaring and rearranging that L, we can see that I'm left with a t squared on the left and a bunch of constants times L on the right, and no y-intercept. So this exactly fits y equals mx plus b again. Meaning that if I graph t squared as a function of L, I should get a line with a slope 4 pi squared divided by acceleration due to gravity. So therefore, t squared versus L is linear with slope 4 pi squared over g. Again, not the only option. You could have definitely graphed t versus square root L, and that would have slope 2 pi divided by root g. But typically, we just don't like dealing with the square roots in there. So we just instantly remove it via squaring. Rules for plotting points and drawing best fit lines, which seems a bit odd that we actually have to review this, but it's definitely worth it. If you're asked to plot points, try to use at least 75% of the grid space to avoid clutter. And also, utilizing a lot of the grid space even earns you a point. So you would not earn one of the 15 points on the question if you didn't use enough of the grid. So usually it's like 50%, they say, but use the space provided to you. Although they really haven't been asking you to plot points recently. They've usually given you the graph. When drawing the best fit line, do not connect the data points. That's not what a best fit line is. Best fit line tries to estimate the data the best by getting half the points above and half the points below the line. Use a ruler. You get one on the exam. Please use it. And also do not assume your line passes to the origin. The y-intercept definitely means something of importance in our models, whether it's 0 or non-zero. And sometimes we want to find that just like the slope. So to calculate the slope of the best fit line is always significant in some way to the model. And you got to calculate it with units. So to determine the slope, sometimes you have to do this now if they just plot the points. You have to just explicitly do rise over run, so y2 minus y1 over x2 minus x1. Explicitly mark the points that you're taking the slope between on your line, so the College Board graders know that you're being a smart human and using points on the line and not just random data points. Do not assume that your line goes through all the data points. If it goes through some, you can definitely use them. But if you're not into that and you feel like getting a more precise answer, although College Board is really lenient with the range that they accept, linear regression on your TI works. It's much slower, but also more accurate. Just state that you use linear regression and write the M and B values. Here's a past example of just a plot that the College Board provided. Best fit line, and also notice they circled points that crossed at nice readable values that they used to get the slope. So notice that none of these data points are actually exactly on the line, so they didn't use any of them for the data. All right, after you do your best fit line and find the slope, you got to relate the slope to the thing we actually want to calculate. So the main point of finding the slope of the best fit line is to actually solve for some desired quantity. So to solve for the quantity of interest, you got to solve a slope two ways problem, where you find the slope of your model. That's before you did the best fit. That's the thing that told you this was a good relationship to graph. So it's the slope in terms of variables. And then you get the numeric experimental value of the slope by actually computing it, using the best fit line or linear regression. Then you set these two equal, and you get a solvable question. The answer is usually not the number that the slope is. Typically, there's a bit of manipulation that needs to go on there. So you should set slope as a variable. So what do you mean by that? Well, let's look at this one. This is another classic type linearization question. Suppose a group of students record the height h. A block of unknown mass slides up an incline. After compressing a spring of constant k, a distance of x, they record the height h reached for a variety of initial compressions x. So h is our dependent variable, and x is our independent variable. The students find a graph of h versus x squared is linear and has a slope of 8.5 inverse meters. So this just says they did the linear regression for us. Solve for the mass of the block, given that k is 100 Newton per meter. So we're actually not given the equation. We know that h versus x squared is linear, but I have no idea what the slope is. Is the slope the mass of the block? Is it 1 over the mass of the block? Is there a pi in there? Is there something else? I don't know. So we got to derive the model. So I know it's going to be energy conservation here because I'm compressing a block against a spring and then I'm shooting it up a ramp. That's clearly spring potential energy getting turned into gravitational potential energy. So I know that the 1/2 kx squared at the beginning is getting turned into mgh, potential energy at the end. And notice I already colored my x red and my h red, because those are the two things that change between each trial. Everything else doesn't, and we can verify, right? They're using the same spring for each trial, so k doesn't change. Same block, so m doesn't change. And same planet, so g doesn't change. And then when we graph, we typically like one of these variables to be solved. And just because we said h was the dependent variable, not like it matters, let's solve for h. So you get h equals k divided by 2mg times x squared. And using our standard color codes, that means that this teal color, k divided by 2mg, is going to be the slope of our model. So h divided by x squared is the rise over run, which is the slope, meaning the slope of the h versus x squared graph is equal to k divided by 2mg in our model. So here's our slope two ways. So variables, the slope is k divided by 2mg. Numbers, students said linear regression got 8.5 inverse meters. And now we just set them equal and solve. So m is just going to be k divided by 2g times the slope. If you set slope equal to k divided by 2mg, multiply both sides by m, divide by slope, and we get this expression. Plug in the set values, and we get a value for m. And that's it. All these problems look like this. Except you are the one typically getting the number too. So this would be the most involved variation where you actually had to come up with the formula yourself too. Last thing is you're probably going to be asked some sort of error analysis. And it's non-trivial. It's definitely not middle school error analysis, like we just forgot to measure the height. it's something more subtle. So most lab-based questions conclude with some sort of a potential error source. If you're asked to identify one, do not say human error. Human error is not a real thing. I agree that humans caused the error, but what errors did the humans actually cause? So some general tips to determine the effect that mismeasuring something will have on the slope or the overall result, look for an equation that relates the slope to that quantity. And how does changing that change the whole thing? So this is all about functional dependence. So for example, the two easiest ways of looking at this is the affected quantity in the numerator? Well, then the two are related. So if one is too small, the other is also too small. But if one of your quantities is in the denominator, oh, and I see this word should be denominator. Sorry about that. Denominator, then increasing that variable decreases the entire expression. So an inverse relationship. So you're really just seeing where does that variable appear in my expression? Is it on top? Well, then increasing one increases the other. Is it on bottom? Well, then increasing one decreases the other. So you have to be on the lookout for both. And if it doesn't appear at all, well, it must not affect your final answer. So suppose that students in the previous problem accidentally used a spring with K equals 80 Newton per meter instead of the value they used in their equation of 100 Newtons per meter. And they did all their calculations without noticing. What effect would using this too large of a spring constant in their math have on the student's calculated value of the block's mass? So we're saying they plugged in a higher K than they should have. Let's think about it. Well, their calculated value of M is actually going to be higher than it should be in actuality. And here's why. The slope of the best fit line has a positive proportional relationship with the spring constant K, meaning K is on top. So if the students used a value of K that was too large, so 100 instead of 80, their calculated value of M would also be too large. And that's all you have to say for justification. So since M increases when K increases, using a too high value of K will also cause the value of M to be larger than it should be. And again, you can think even with the test numbers that this would work, right? If you plug in 100 for K, it's going to be bigger than if you plug in 80. So that means their calculated value was too high. And that's about it for linearization and the lab-based question. So a question might not contain all of these components. The actual designing part is probably the most rare, but the deriving a model, linearizing, solving for the quantity of interest, and then interpreting error, that is very common. Now, hopefully, when this shows up on your exam, it looks a bit more familiar on how we actually solve these problems.